suppose that now we have some additional external force, so applied to the spring mass system. Right, so then this external force is accounted for by an extra term in the equation, plus f of t. And so remember that this whole equation, in this form, still this is Newton's second law of motion, which tells us that mu double prime is the force, and in the right hand side we are trying to list down all the forces that act on the spring mass system. Right? So now, without the external force, it is just minus gamma u prime minus ku, and now, as we have our external force, we have to add plus f of t. Right? Usually it is a periodic function, and we are going to try to look into the case when this periodic function is f0, some number, times cosine of omega t. Right, so this omega is the frequency of the external force. The frequency of the external force. And here is our equation. A little animation for you. Right, so for example, here, let me make damping smaller. So let's play it. So the external force is this this moving thing on the left, and the spring mass system is on the right. Right, so you can think of the external force as just when we try to indeed to move the position where the spring is sits at. Okay. But what's going to happen if, say, so let me make the damping very small. So let's say maybe 0.1. So here the frequency of the driver cannot be changed into this, but we can change the frequency of the spring mass system, right? So what happens if we make the frequency of the spring mass system to be exactly the same as the frequency of the driver? And here is what happens. So when this mass naturally moves to the left, the external force tries to move it further to the left. When it moves to the right, the external force tries to move it further to the right, and so on. And then it repeats, and here we have a resonance. So the whole system is just, oscillations become too big. Right? So let us look at the case when there is no resonance first. Right? So here is the equation. Recall that, maybe I should write it down, that omega 0 is actually the frequency, is the natural frequency of this. The system is going to be square root of k over m. So here is the general solution of the homogeneous equation. It is here, square root of k over m. Then, just in case, let us. We need the Wronskian to find the solution of the non-homogeneous equation by the variation of parameters. So here is the Wronskian is just omega 0. It happens to be the frequency. So a little problem for you is to try to apply variation of parameters to find a particular solution of this equation. However, if you just look at it, you can figure out that you can try to find a particular solution in the form where it is some number times cosine of omega t, and it is going to work. So you just need to find the right number, and just by trial and error. And it happens that a particular solution is given by this formula. You may wonder why we have to assume that omega does not equal to omega 0, and the reason is because if omega were equal to omega 0, then this is square root of k over m. Then this denominator would be minus m times square root of k over m squared, so which is k over m plus k, cancels out, minus k plus k is 0. So if the frequency of the driver were the same as the frequency of the natural frequency of the spin and mass system, then it would cause this denominator to vanish, right? And then it wouldn't be defined. It wouldn't make sense. So this formula only makes sense if we assume that omega does not equal omega 0. And then we have our general solution of the ODE. And again, you can try to see that the solution of the initial value problem is given by this formula. Well, and finally, if you want, you can play. Again, I made a simple animation for you in Desmos calculator, so you can click here and